morning, Angela.
Good morning.
How are you today?
I'm good. How are you doing?
Just fine. Okay, so ready to start your day off with some GRE questions.
I am.
Okay, let's look at number one. These are in a category called discrete quantitative questions. And I apologize for the blurriness of it. If you can't read anything there, here, let me read it out loud. Evan has 4 times as many books as David and 5 times as many books as Jason. If Jason has more than 40 books, what is the least number of books that Evan could have? And what I think would be helpful if when you see these kind of questions, the first question you want to ask yourself is, how am I going to solve this? Which of the 3 ways am I going to use to solve this? Am I going to do it algebraically? Am I going to back solve it? Or am I going to pick some arbitrary numbers?
Okay, and pretty much what I did was, well, what I started doing is since Jason has more than 40 books, I just went ahead and went with 41.
Okay.
And then David has 5 times as many, so he has at least 205.
Okay.
And then Evan has 4 times as many, and that's not going to work.
Okay.
Or is it?
So what would you try next?
I don't know.
Well, this is a classic back-solving problem.
Okay.
Okay, and in other words, if we approach it, from the moment we look at it, we're going to back-solve this. And since it says what is the least number of books, we're going to start with A. In other words, you don't always start with B or D. If the question is least number, you start with the lowest. If the question is highest number, you start with the highest, obviously. So 200 you've already ruled out because that would mean that Jason would have exactly 40. In other words, if you go through the math, if Evan has 4 times as many as David and 5 times as many as Jason, could he have 200? Well, David would have 50, Jason would have 40. That's not enough. He's got to have more than 40. At this point, you realize that the number would have to be 205, but it has to be evenly divisible by both 4 and 5. Since 205 isn't, let's check 210. Well, I know 210 is not divisible by 4 because for a number to be divisible by 4, its last 2 digits have to be divisible by 4. In other words, 610 I know is not divisible by 4 because 10 is not.
Okay.
620 or 616, I know that's divisible by 4 because 16 is. So I know it can't be 210. And the moment I find 220, okay, that's divisible by 4. It's also divisible by 5 because any number ending in a 0 or a 5 is divisible by 5. So that's got to be it. Without even having to go through and figuring out how many David has or how many Jason has at this point, we realize that we're looking for a number that is divisible by both 4 and 5.
Okay.
There's a few other number theory things. A number is divisible by 3 if the digits add up to a number that is divisible by 3. In other words, 1 plus 6 plus 2 is divisible by 9. So 3 has to go into 162 evenly. Or 3 has to go into 1611 evenly. 4 and 5, those are the key ones to know. How to quickly figure out whether a number is divisible by 2, 3, 4, or 5.
Okay.
All right. She goes to the National Gallery once each month except July and August. No, she doesn't go in July, and she's going to go 3 times in August. Single admission costs $3.50. A pass valid for unlimited visits in any 3-month period can be purchased for $18, and an annual pass costs $60. What's the least amount in dollars that Judy can spend for her number of planned visits? Now this one, obviously, there's no back solving to be done. There's no picking numbers to be done.
No, it looks like it needs to be solved algebraically.
Well, algebraically, but there's no quick way to do it algebraically, purely algebraically. What you want to do is go through her options. She has basically 3 options. She can get an annual pass. That's one option. She can pay individually for every time she goes. How many times is she going over the course of the year? She's going,
16.
actually, she's going 3 times each in July and August.
Right. So 16.
Okay. So individual charge would be, annual pass is 60. Individual is 16 times 350. What is that?
56.
Well, that's cheaper than the annual pass. And what's the third option?
3-month period for $18.
And clearly she would take the 3-month period that covers July and August. So it would be $18 to cover 7 visits. Plus you would have how many at the individual rate?
9.
So 9 times 350. And let's have you do these since you need to practice doing these calculator problems quickly. Probably do you have an online computer calculator, or you have a hand calculator in front of you, or what do you use?
Hand calculator.
Okay. As you get closer to the test, you'd probably be well served to put a calculator on your desktop and use it, just because that's what you have to do during the test, correct?
Yes.
I mean, you're not allowed a hand calculator, so you'll have to use them. If you're using Windows, Windows has a calculator that you can use. It's probably going to be as close to what you see when you take the test. And there is a little difference. I noticed that it's a lot harder for me to use my smartphone calculator than it is a keyboard, just from the differences in the virtual keys. Of course, you'll be using a keyboard, won't you? Yeah.
Yes.
Okay. So probably won't.
Okay, so it looks like the answer would be $49.50.
That's correct. Okay. An age problem. I've been dying to get to the age problems because age problems are the textbook back solve. Whenever I'm doing a back solve problem and I want to illustrate what's the perfect problem for back solving, it's always age problems. And the reason is is because not only will your first guess tell you whether it's right or wrong, but it'll tell you automatically whether it's too young or too old. And it will be completely unambiguous. It'll be absolutely clear to you. So work me through how we're going to back solve this.
Well, once again, start with either B or D.
Okay.
And let's see, since Allison is now 3 times as old as Jeremy, then let's see.
Don't spend a lot of time figuring out whether it should be B or D. Just start with one of them. Yeah.
Okay.
So we're going to start with what?
B.
Okay. So assume 12.
So that would have made, let's see, Allison is now 3 times as old as Jeremy, so that would make Jeremy 3 or 4. But then let's see, 5 years ago she would have been 7. So that won't work.
Okay. So we know which way do we have to go?
Up.
Yes, absolutely clearly. So what's the next thing to try?
We'll try 30.
Okay.
So she's 30 now. Let's see. That would make Jeremy 10. And then 5 years ago, she would have been 25, which is 5 times, so that's the answer.
Okay, good. And had that not been the answer, you would know what the answer is. It would either be C or E unequivocally. Interestingly enough, the book suggests that you start with C. And they are absolutely wrong. I've worked out the math of it and the probabilities of it. And if you start with B or D, you're going to get the answer correct 40% of the time on your first trial, because you're going to know it. If it's either B or A, you're going to know it. And if you work through the probabilities of starting with C, you don't get as good as, in other words, you're trying to minimize the amount of math you have to do. And you're better off from a probability point of view starting with B or D than you are with C.
Okay.
It's the largest prime factor of 255. Our choices are 5, 15, 17, 255. How are we going to do this?
Break it down into the prime factors.
Well, I'm going to suggest that that's not going to be your quickest way to do it.
Okay.
Because that's quite a bit of work. Why don't we back solve it? Starting with the largest number. Is 255 the largest prime factor?
No.
Is 51 the largest prime factor?
No.
Is 17?
Yes.
Bingo.
Okay.
We don't have to go through that process of breaking that down into 5 times 51 and that times 17 times 3. I guess we'd get it rather quickly if we did that process. But I'm a huge fan of back solving. I'm almost always going to suggest back solving if there's a choice of methods. I'm that fond of it. If C is the product of A and B, which of the following is the quotient of A and B? Am I going to solve this?
This one I'm not sure.
Algebraically.
Okay.
Absolutely. I mean, I suppose we could pick numbers. That might not be a bad idea. But if you're going to pick numbers, picking numbers is always a combination of picking numbers and back solving. And that actually would work here. We could pick numbers for C, A, and B, and then figure out what the quotient of A and B was, and then figure out which of these answers match that. But on such a simple algebra, let's just try looking at it algebraically. C is equal to AB. Well, which of the following is the quotient of AB? Well, what would I have to do to get A divided by B? To both sides of this equation.
Divide both sides by B.
Well, that's a start. We could do it in one step, but I don't mind doing it in two steps. So that gives you A. So now we have C over B equals A. And notice, look at our answers. Every answer has a C and a B in it.
I know A.
Our answers are functions of B and C. So what do I need to do to get A over B? Let's divide both sides of the equation by B again. So there's your answer. A over B is equal to C over B squared. Now, when I said we could do it in one step, what I meant was we could divide, whoops, hold on. We could divide both sides of this equation by B squared immediately. Notice that that gives us A over B. So I'd be far more inclined to solve this algebraically for me. That's because I spend 4 hours a day working with algebra. For somebody that isn't that familiar with how to construct A over B, if you ran into a problem here, then let's just use this as an example of how we would pick numbers, even though I don't like picking numbers on this just because I think it's longer. But if you ran into a jam and you couldn't figure out how to construct A over B, help me through what would the process be if I were to pick numbers to try to solve this? Again, I'm going to turn my...
I guess just A equals 1, B equals 2.
Hold on, excuse me a second. I don't want to end this meeting. I just want to turn my camera off because my computer is complaining again. Okay, excuse me. Okay. I had a student once who was taking GMAT, and I said, whenever you're going to pick numbers, don't pick 0, and you can pick 1, but don't pick 0. And he spent the next 2.5 years convincing me that you could pick 0 just fine. In other words, he had one of those personalities where he was determined to figure out why you couldn't pick 0. So he picked 0 every time we ran up against a problem, and never once did we have a problem with it. Although I suppose if you had to divide by A, you wouldn't want it to be 0. But even here, the quotient of A and B is going to be A over B. Since it's going to be A over B, how about we pick a bigger A than a B? Let's do A equals 2, B equals 1, and the reason I do that is because I want the answer to be a whole number, not a fraction. If I let A equal 1 and B equal 2, then this is 1/2, and I have to find out which of these is going to be 1/2, which is a harder job than figuring out which of these is equal to 2. Okay, so there is a little bit of rhyme or reason when you pick numbers. So A times B would equal C. So 2. So which of these answers equals 2? Is this going to be another one of these where, no, were they all equal 2?
Hopefully not.
No, really. Let's hope we don't run into one of those immediately again. Well, certainly A doesn't equal 2. B does.
Yes.
We better check a few more.
No.
No.
Oop.
No. Yes.
Uh-oh.
E and B. So we're down to B or E. Well, let's go back and pick numbers, and this time we do not want to pick 4 and 2. Let's make sure we change that fractional relationship, and in fact, let's pick 3 and 2. No, let's pick, this is an interesting question. Let's see, B is C over B squared. If I pick 3 and 2, I have a fraction. But that may not be that bad. Let's try 3 and 2. If nothing else, it's going to answer the question for sure, even if we do have to deal with fractions. So the quotient is 3/2, and C is 6. So with A, B, and C of that, which one gives us 3/2? Let's check B. 6 over 4 is 3/2. Let's check E. We can immediately tell that that's not going to be 3/2. That's going to be a whole number. So it didn't involve, okay, here's a point. We want a whole number when we do it the first time because we're going to have to make 5 calculations. Once we've narrowed it down to just 2, now I'm less concerned with the amount of time and the calculations I have to make, and I'm more concerned with choosing a different set of multiples. I do not want to choose 4 and 2 because that gives me that same 2-to-1 relationship. Not necessarily that that would be wrong, but I know that 3 and 2 is going to precisely give me the answer. And yes, it means the quotient is 3/2, which is a fraction, but not that hard to deal with. When I do this, when I get 6/4, that's 3/2.
So yeah, it would just be easier to do it algebraically.
Much easier, much easier. Although I am starting to get surprised at how many of their pick numbers problems. Here's another one. This is a very typical one where most likely you've got a combination of multiplication and division going on. Now, maybe, I don't know, let's look at this. It's maybe worth giving a cursory glance as to the algebra of it to see whether we could set it up in our head. But quite frankly, if you're like me, you get quickly confused, and I'm not positive. Whether I'm going to be multiplying, dividing, I've got to convert cents into dollars, so I know there's going to be 100 involved there. And I don't know whether it's in the numerator or the denominator, so immediately I'm pick numbers on this one.
Okay.
Okay. So what should our widgets cost? How many widgets for how much in cents? And how many would you get for some number of dollars? So pick a W, a C, and a D that you can figure out in your head how many you're going to get for those amount of dollars. And I'm going to suggest using different numbers. Don't use 10, 10, and 10.
Yeah, I don't even know where to start.
How many widgets should we have?
2.
How much should they each cost?
A penny.
That's fine. How many would you get for $1?
100. 50.
You'd get 50. So our answer is 50 based on those 3 numbers. Now, I'm not sure I would have picked 2, 1, and 1 because 2 of your numbers are both 1, but that's okay. Let's see what happens. So we want to plug in these numbers for W, C, and D and see which answer is 50. Is it A?
No.
Is it B?
No.
Is it C?
No.
Is it D?
No.
Must be E. Done with problem. It's not E either.
No.
What the heck's going on here? Did I do something wrong here? Let's see. We got 2 widgets for a penny each. I'd be able to get 50 of them for $1, right?
Yep.
You got 100 cents. You got If 2 widgets cost notice, again, I made the same kind of mistake I made the last time we had one of these problems. I set it up wrong. 2 widgets cost 1 cent. That means each widget costs a half a cent.
Ow. Okay.
You see where we did?
Yep.
So we don't want to use 2 and 1. We
No.
could use 2 and 2. Then we'd get 100 for $1. If 2 widgets cost 2 cents, each widget costs a penny, and we get 100 of them for $1. Now, if we go through this math and figure out which of these equals 100, it's not that, it's not that, it's not that, it's not that. It's this, A. The D and the W multiply to 2, divided by 2, they cancel out, that's equal to 100. So the process is not the problem here. The picking numbers and solving it is the easy part. The hard part is figuring out their language and interpreting it properly. I've made the mistake twice where I read in an each. In other words, when I read this, I read if W widgets cost C cents each, how many widgets can you get for D dollars? But that doesn't really make sense. And it's all you have to do is read it accurately and don't throw in the each like I did. And we would be able to figure out how much each widget cost. And then it would be easy enough to figure out how many widgets you'd get for D dollars.
Okay.
Okay? But at least on that one, once we got it structured correctly, there was only one answer. We didn't have to deal with multiple answers were correct. And you don't usually. That's actually a rarity. And in fact, the one we ran into last time where there were 3 answers or 4 answers correct, and then you picked other numbers and there were still 2 answers, that's the first time I've ever seen that come up to that extent.
Yeah, that was strange.
Yes, it was. Okay, this one says if 120% of A is equal to 80% of B, which of the following is equal to A plus B?
Once again, pick numbers?
Well, before we decide which method we're going to use, let's write out what that means.
Okay.
1.2 of A equals 0.8 of B. And they want to know what A plus B is, but notice all the answers are in terms of A. So if we solve for B and substitute it, we'll get the answer. So algebraically, might not be so hard here. How do we solve for B? How do we solve this equation for B? It's basically the last step in solving every algebraic equation. Is you've got B almost fully isolated. What do we have to do to get it completely by itself?
Well, divided by 0.8.
Okay. So now B is equal to what? What is that? That's one that's
0.15.
1.5, right? Did you say 0.15 or 1.5?
0.15.
It's actually 1.5.
Yeah, 1.5, okay.
And let's talk about ballpark checks here. I've been a proponent of ballpark checks my entire life. In fact, it caused me to completely do math a different way. And it's because every time I had a problem like this, I always checked to see if I'm in the right ballpark. Can a bigger number divided by a smaller number be less than 1? No, it cannot. So if I get an answer like 0.15, I'm off by a magnitude of 10. There's no way that a bigger number, 1.2, can be divided by a smaller number, 0.8, and be less than 1. So I know my decimal point's off. So that decimal point's got to go right there. So it's 1.5A. So that's what B is. So now what is A plus B? We have A plus 1.5A. That's equal to what?
I'm sorry, I'm trying to write this down as we're going along here.
Okay.
Okay, so A plus 1.5A would be 2.5A.
And that's the answer, C. So this problem was very definitely more easily done using algebra, but perhaps that's for me only because I do so much algebra once again. Picking numbers would also work, but I think picking numbers is harder here. Let's look at picking numbers. Regardless of whether you're going to pick numbers or solve it algebraically, I think it's worth writing out that statement because I can't even decide which I want to do until I write that out. And then I can figure out, well, how hard is it going to be to solve algebra? Not that hard at all. Solving this algebraically is really quite simple. Picking numbers, on the other hand, is a little tricky. What numbers would you pick for A and B to make 1.2 times A equal to 0.8 times B?
Okay, yeah, that is trickier.
Well, here's what the book does. They say let A equal 80 and let B equal 120. Then you would have 1.2 of 80 is clearly the same as 0.8 of 120. You can see why that's the same as that?
Uh-huh.
Okay, it's a little harder to figure out to pick those numbers because of it. But if you see that, still is not that easy. Well, we know that A plus B is now 200, but that doesn't match anything over here. Well, what is all the answers, since they are some number times A, and we know that this times 80, if I let A equal 80, we have to find 200 over here, and that happens when A is equal to 80. 1.5, excuse me, that happens when A is, the answer is C. In other words, if we divide this by 80, what A is, we get 2.5. Picking numbers is a lot trickier with this problem. In my mind, figuring out how to solve that by picking numbers is probably twice as hard as figuring out how to solve it just algebraically. All right, let's go on to the next page. Number 8, a shaded area problem. What are shaded area problems again?
Those are the ones where we figure out the area and deduct the...
They're subtraction problems.
Right.
That's what I like to think of. The moment I see a figure, the moment I look at this, I know it's going to be a subtraction problem. And what is it I'm going to subtract? What from what?
You're going to subtract the unshaded regions from the shaded.
Well, from the outside, not from the shaded, because I don't have any way of figuring out these shaded areas. Those are very unusual looking shapes. We don't have the geometry to figure that out directly. However, if we take the outside square, which is we know how to do very easily, and we subtract out these 4 semicircles, we will be left with the shaded area.
Okay.
So what's the area of the outside square?
Both sides are 12, so it's going to be 144, the area.
Okay, that's not much help since 4 of those answers are 144. In other words, that doesn't narrow it down a lot, so we do have to finish the problem. And the diameter of each of these semicircles is 8. So what's the total area of the 4 semicircles?
Okay, well, okay, I'm looking for the area of each semi.
Right.
Okay, well, the area of each of those is going to be 16 pi.
Okay, be careful. They're semicircles.
Right.
So the radius is 4, so it's 16 pi for the whole circle, but the semicircles are each 8 pi because they're half of that.
Right.
And then there's 4 of them. And I definitely recommend doing that in 2 steps.
Okay.
Not trying to do the whole thing at once. In other words, we don't want to be having to do a pi 4 squared over 2 for the semicircle times 4 because there's 4 of them. Don't do that first. Is all it will do is get you into a confused state. And I think, in other words, I'm also a firm believer that if you don't want to make mistakes on this, you do it in separate steps. Let's figure out precisely what the area of that semicircle is before we decide that there's a total of 2 circles here. You see what I'm saying? The difference?
I do.
That's a minor point. The key thing is to know that the radius of each is 4. So, okay, the area of one circle would be that. If I wanted to say I have 2 full circles, okay, I can jump to that. I can do it that fast. That's okay.
Okay.
But there's a trap in there if you're not careful, in that you say, okay, I've got 2 circles, diameter of 8. I'll just use one circle with a diameter of 8, so I'll make it 8 squared pi, which would give you 64 pi. There's a lot of traps you could fall into if you tried to do that too fast. Okay, x and y are integers such that x cubed is equal to y squared. Which of the following could not be a value of y squared? Is that what that says? I'm just looking at my book, make sure that I didn't...
So yeah, it's a little blurry.
No, that's a question mark instead of a squared. So
okay.
What can be the value of y? What can y be? Well, this looks like a classic back-solving problem, especially since we need all values. Whenever you get a question, we need all values, just know that you're going to have to go through every single one of them. That's the only way to solve it. We could try to do something algebraically, but since we've got a y squared and there's going to be plus and minus involved, let's just start with 1 and work our way through.
Okay, so if y were the value were -1,
okay,
the y squared is going to be 1, and x cubed is going to be -1.
Actually, let's do it. X cubed is going to equal -1 squared, which is x cubed, that's a positive 1. So actually x is 1, which is okay. But I want to make sure we go through this math properly. We're squaring a -1, that's why it makes it positive.
Okay.
But notice that if x cubed is equal to 1, x can't be -1. X can only be 1, because if x were -1, x cubed would be -1. So this does give you a unique solution. Yes, x could be 1. And our only restriction is that x and y have to be integers. So as long as we get an integer, not an irrational number like square root of something, we'll be fine. So A works. How about B?
Yeah, I don't think I understand this one.
Okay. Can y be 1? In other words, let me give you another one. Could y be 3? Could x cubed equal 3 squared with the restriction that x has to be an integer?
No.
Right, because then we would have x cubed equals 9, and x would be the cube root of 9, which is not an integer.
Okay.
So that's what they're saying. So one of these numbers, or some of those numbers, are going to give us that problem. And this would almost be easier if we'd have started from the other direction. No, not really. Let's just keep proceeding. The only reason I said that is because if we would have started with a number that it couldn't be, that would have been good. It would have helped explain the concept of the problem to us. Because I agree that this is difficult to understand, what they're really asking for. I had trouble when I first looked at it. And I just kind of had to start somewhere. Yeah, start with an answer and see if I could work through it. And okay, yeah, if y is -1, then x is 1. They're both integers, so yes, y works. So does 1 work? Well, let's see if y were 8. What would x cubed be equal to if y were 8?
4.
No, if y were 8, 64.
Oh, 64.
8 squared. Is there an x? What is x if x cubed is equal to 64?
That would be 4.
That's an integer also, so that works. So A, B, and C work. Let's try 12. What would x cubed be if y were 12?
144.
On this calculator you're going to have, does it allow you to do cube roots?
You know what? I'm not even sure. I know it lets you do square roots, but I'm not sure about cube roots.
Probably not. I'm looking at a little sun-powered calculator here, a real cheap one. And it's got a square root symbol on there, but it does not give me any way to raise anything to a power. And the one way to do cube roots would be to raise it to the 1/3 power. So you're probably not going to be able to use a calculator to answer this. Question is any number cubed equal to this?
And I don't believe so.
You're right. There isn't. Let's find, rather than an I don't believe so, let's test a couple.
Okay.
We know that 4 cubed is 64. Well, what's 5 cubed?
125?
Yeah, that's a good one to know, actually. That immediately tells us that there's not going to be a number, a whole number, that when cubed is equal to 144, because 6 cubed, that's 36 times 6, that's 216.
Okay.
Now, you could do these on your calculator.
Right.
But you can't do 5 cubed, but you can say 5 times 5 times 5, or 6 times 6 times 6. So you could conclusively prove that there is no integer cubed that's equal to 144. So that's not a possibility. About 16 cubed.
16 cubed.
No, oops, excuse me. Yeah, that's 256 is y squared, which means is x cubed 256. Does that work? Let's see. You said that 6 cubed was equal to 216. That's 36 times 6. Yeah, that's 216. So clearly 7 cubed is going to be way more than 216.
Right. So
it goes fast. In other words, we went from 125 to 216 with one number increment. So there's no way that 7 cubed is not going to be way bigger than 256. So that doesn't work either. 27 squared.
729.
What else? How else could I write that? Let's see. It was 27 times 27.
Oh, well, yeah, you're going to have 3 cubed equals 27. Or, yeah.
You're on the right track here. I could factor out that 27 into 3 times 9. This one's 3 times 9. Now I multiply the 3's. I got 9 times 9 times 9.
Right.
That's equal to x cubed. X could be 9.
Right.
So that does work. And however you have to do that, I'm sitting there trying to think, you can get this on the calculator, but then going from this to determine whether the cube root, I suppose the only possible choices would be 8, 9, or 10, because 10 cubed is 1,000. That's way over that. I know it's not that, because it's an odd number. Could be that. 9 times 9 is 81, and then 1 times 9 is going to give you a 9 as your last digit. You see what I'm kind of doing here?
Yeah.
7, well, 7 times 7 ends in a 9, and then 7 times 9 is going to give you 3 as a last digit, so it's not 7 cubed. So I've eliminated 7 cubed, 8 cubed, and 10 cubed. The only one I really have to check is 9 cubed, and I can do that on a calculator. 9 times 9 times 9, I'll get 729. I'll know that's the answer.
Okay.
So even with a minimal calculator, you can still use it to your advantage on this problem. Although it actually might be easier seen if you take that 27 times 27 and break it up into 3 times 9 times 3 times 9. I don't know.
Yeah, that looks easier to me.
It seemed like that's the way your mind was kind of working on that. And if that's the way your mind's working, by all means do it that way. Not everybody would be good at making that leap. But okay, what is A divided by A% of A, question mark? So again, before we can decide whether we're going to do this algebraically or pick numbers and back solve, we could clearly do that. In other words, it's clearly a pick number and back solve type problem. It's just not clear that that's the fastest way to do it. Okay? When I say it's clearly a pick number and back solve problem, that's because we have nothing but variables in the question, and we have answers that have variables in the answers. And that is what you look for picking numbers and back solving. You can almost always solve those kind of problems like that. But before we do that, let's at least write the algebraic expression. So what does that mean?
It's going to be A divided by A% of A.
Okay, how can I write A%? In other words,
100.
well, I can't really do that in an expression. So I have to convert that to a decimal or a fraction. So what it really is A divided by 100, if you think about it. In other words, if I said 5% and I want to write that as a fraction, I'm going to want to write that as 0.05. Well, how do I get that from the number 5? It's by dividing it by 100. So that's A%. Of means multiplication,
Of
so it's
A.
that. So there's our algebraic expression, which we would need to do regardless of whether we were going to pick numbers and back solve or solve it algebraically. And that's actually pretty easy to solve algebraically. We're going to have to solve this whether we pick numbers or not. In other words, there's no way picking numbers could speed this problem up. It could only slow it down. Since we have to do this math, I mean, I suppose I could pick a number for A and solve it and then find out which of these equals that number. But is that necessary to do?
No.
Okay. So what's the answer?
So the answer is going to be 100 over A.
Good.
It's going to be A divided by A squared divided by 100.
Right.
Invert the A squared over 100 and multiply by A.
Well, now hold on. Let's just, okay. So let's make sure we got the algebra right here on how to do this. So the bottom becomes that, right?
Uh-huh.
And we do this by flipping the bottom and multiplying.
Right.
So this problem is the same as this.
Right.
That's what you were doing? Okay.
Yes.
And then that a cancels out with that exponent, and you're left with just 100 over a. So, yeah, by all means, this is an algebraic solution,
Okay.
which is interesting because the book actually gives a pick numbers solution. They do.
Yeah, so far the way you've been showing them makes more sense. It's quicker.
Well, it definitely is here, because if you pick numbers, you still have to set it up and you still have to solve it.
Right.
In other words, it doesn't really take away any work. So it only adds work. But that first part is the tricky part. And that's something good to learn. Because you're going to be faced with that. Again, this is not the first time they're going to give you X% of something, and you have to put it into an equation, and in order to put it into an equation, you've got to eliminate the percent sign.
Okay.
If an object is moving at a speed of 36 kilometers per hour, how many meters does it travel in 1 second? I'm rewriting it. I'm rewriting it on the left because this conversion problems,
Yes.
I think there's a certain methodology that you always want to use. Now, if you're good with these,
No, I'm not.
okay. Well, we want to end up with meters per second. So I need seconds in the denominator. So what conversion factor that relates seconds to hours, where hours is in the numerator? Because I want the hours to cancel. So if I have 1 hour per how many seconds? Well, that's hard to do, but I know that it's 60 minutes.
Right, which is, and then times 60.
Okay, the next factor is 60 minutes. Excuse me, 1 minute per 60 seconds. And then the minutes cancel. And the goal is to get seconds in the denominator and meters in the numerator. Well, right now I'm here. I got 36 kilometers per 60 times 60 seconds. That's where I'm at by the time I get to there. So what one more conversion factor is going to allow me to get this meters per second?
We need to multiply the 36 by 1,000.
We need to get rid of the kilometers.
Right.
So we need in our conversion factor, because each of these conversion factors can be reversed. In other words, I can have 1 kilometer per 1,000 meters, or I can have 1,000 meters per 1 kilometer. Well, clearly I want to get rid of the kilometers, so it has to be in my denominator. And that's the secret, is set all of these conversion ratios up in the correct numerator and denominator. And that's all you need to do so that they cancel. In other words, my kilometers cancel and I'm left with meters per second. So now it's 36 times 1,000 divided by 60 times 60. Okay. Now, you might think the easiest way to do that would be a calculator, but I don't personally think so. I think I would do this. I would cross off that 0 and that 0 with those 2 zeros, and then I would have 36 divided by 6 is 6. 6 times 10, whoops, that 6 gets divided by that 6, and I've got 10 left.
Oh, okay.
And 10 meters is the answer.
Per second. Okay.
Yes. but you don't need, let's see. The heck? Oh, that was just a second. I'm looking to see. When I photographed this, they didn't have, they must have meters per second under that. I'm just not seeing it. Yeah. In other words, the answer isn't meter. Oh, yes. How many meters does it travel in 1 second? The answer is 10 meters.
Okay.
So the answer really is 10 meters per second, but since they've asked in 1 second, the answer is just 10 meters. So, okay, why don't we end with that question, and we can pick up with 12 next time. Yeah, I like these, all of these practice exercises related to specific parts of the GRE. The next practice test is concerning the comparison, limit comparisons, or direct comparisons, whatever they call that.
Okay.
Direct quantitative comparisons. So.
Okay. Well, thank you.
You're welcome, and I will talk to you the next time.
Okay. Bye-bye.
All right, Angela. Bye-bye.